As energy efficiency becomes more and more important in buildings, in commercial buildings in particular, so highly glazed facades have come in for a lot of stick. So is there an optimum relationship in daylit buildings between solar gain, thermal insulation and energy performance? Today we're delighted to have Andrew Hall, leader of global facade engineering at Arup here in London, to look at the environmental performance of facade engineering. Right, so thanks Andrew for allowing us to come to your offices to talk to you about this. Let's just jump straight in. The facade of a building is roughly 15% of a total building cost. So if there are cheaper options, how do you justify those sort of costs to clients?
The cost of a building is relative. You have to look at appropriate expenditure. So there is obviously initial capital cost for a client, and 15% is a big expenditure. Sometimes it can actually even go up to 20 and 25% of a build, depending whether you're looking at shell and core or total fit out and how complex the facade is. So what we try and look at is appropriate spend on buildings and making the design appropriate so that it's no longer trying to solve the architectural whim of the designer, but it's more about the performance and the comfort and the well-being of the occupants, and that we're now moving much further towards performance-driven design of the skin of buildings.
And what sort of timescales are we talking about? Take a building, when do you get involved and how long does it take?
Well, we try and get involved at the earliest stage possible, because the conceptual thinking of a facade has to be at the very early stage of the architectural design. The facade is often, and the form of the building is often interrelated, and the architect can't come up with a concept if he doesn't know how to realise that concept. Neither can he come up with a concept that won't meet the regulations and the codes. So at a planning stage, there's no point having planning permission for a building that will struggle to meet the codes and the regulations. And also there's no point producing a conceptual design which is very expensive to realise.
The environmental issues, the environmental performance of building facades is much more important today than maybe 5, definitely 10 years ago. So can you just explain some of the developments in environmental performance that you've been working on?
I think that you can look at it at 3 levels. First of all, the code and the regulatory environment. So codes have become more and more onerous as governments and institutions have targets to achieve in terms of carbon reduction, in terms of how they meet their energy commitments as a state or as a region. Then in response to those codes, clients then have to try and define a brief that allows them to develop a project and procure a team and procure the building that meets those codes. But the teams now have to be much more intelligent about how they challenge that brief, because the brief is one of the first things that actually sets some of the preconceptions of how we might solve the environmental performance of a building. Then finally, the third area is obviously the products themselves. As we've become much more focused on performance, whether it's daylight or solar gain or thermal performance more generally, the product and evolution of new products has really not kept pace with the more and more onerous requirements in terms of U value, in terms of thermal performance, in terms of daylight transmission. And the industry continues to look at aluminium and glass as its raw palette of materials, but there is a ceiling at which those materials and those systems will achieve, after which you have to go back to first principles and start looking at the facade more as a wall with windows on it rather than a frame with glass in it. So as we reduce glass, the approach of aluminium stick systems and unitized systems with glass infills becomes less and less the natural response, and more we move towards walls with windows.
Right, interesting. When we're talking about thermal gains in buildings with highly glazed facades, obviously brise layer everywhere. We all know about solar gain, but what's the ratio or relationship between solar gain and just internal heat generation within a building?
It all depends fundamentally on the type of building. Certain buildings are net heat producers and certain building types are net heat losers. So an office typically is generating heat, and a residential building would typically lose heat. So the U value part of a building and its heat gain and heat loss, it depends on the function of the building and the massing and the orientation of the building, as we've said before. If we look at internal gains, what's interesting is buildings, the heat gains in buildings are becoming more and more affected by the efficiencies that are generated by light fittings, by computers, by boilers and mechanical systems. So the gains are reducing of the plant and the light fittings, and the only static is obviously the occupants, which buildings aren't becoming any more or less densely occupied, but the mechanical and lighting systems are becoming more and more efficient and therefore less heat producing.
So since you do a kind of a much more holistic assessment of buildings, are U values less important?
U values is part of the equation. As we become more sophisticated, we realise the obvious, that buildings exist in a dynamic environment and they're occupied in a dynamic way by their occupants, which their use and how they use the building changes during the course of the day. And so we're moving from where the analysis was driven by the glass industry of how do they sell glass through centre pane performance, realising that through analysis we can look at glass and its framers' total system performance, through to then looking at more dynamic analysis where we can change the thermal performance of a facade during the course of the day by dynamic systems, by user control systems, and by better user interface, because the more control people have of their environment, the more tolerant they are and the more understanding they have of the energy consumption of their buildings. A green building, an environmentally excellent building, is not one that is designed excellently, it's one that is functioning excellently.
Okay, Andrew, look, just why don't you show us a couple of examples, work examples of how you analyse the thermal performance, energy performance of glazed facade systems.
We look at the sun path around a building, and then from that we can analyse the total irradiation, the total energy on the facade. And then that allows us to start understanding the energy input, and from that we then try and look at the layers of the facade that we need to put in place to moderate that environment, either statically or actively. So from a static point of view, it's obviously the orientation and the apertures on the facade. From an active point of view, it's then the shading devices, whether they're internal or external. It's good to look at an extreme environment just to make the point. And this is a project with 2 towers in Abu Dhabi where we're looking at how the building sits in its context and in relationship to the sun that passes around it. Understanding how the sun passes around a building allows us then to look at the total irradiation of the sun on the facade. And here you can see the complex model that takes the total energy for each element of the facade during the course of a year. That then allows us to understand what we have to do to moderate that solar irradiation by looking at the 3 layers we fundamentally have in a facade. The external shading around the outside of the building, the glass, which here is in blue on the diagram, and then the internal shading within the building. So we take the context of the project in Abu Dhabi. Obviously we're in the Middle East where we have extreme temperatures of 46 plus degrees and very cold temperatures at night. We also look at the humidity because that affects issues about condensation, and we take a total view through the year of what are the extremes, pluses and minuses, of both humidity and temperature. We also then have to look at wind, because wind and dust and sand in the Gulf have an impact, but similarly they would have an impact in a European context where the environments are actually becoming more extreme. What we're noticing is, climate change is a much talked about topic, but actually we are noticing is more extremes of temperature, of wind, of gusting, which are affecting how we view the building, not just in the short term, but in the longer term of performance through its 25, 30-year life. We dive very quickly into both 2-dimensional cuts through the elements, understanding the glass to glass, the vision areas, and the glass to spandrel areas here, where we look at the temperature contour through and the temperature distribution through the glass and the framing and the spandrel elements to ensure that in different environmental conditions and different relative humidities, we're avoiding condensation and we're getting continuity of the thermal line. So here you can see in red the thermal break between the internal aluminium box frame that supports the curtain wall and the outer glass or the spandrel of the curtain wall, and that thermal break stops the heat or the cold from the outside passing through to the inside. And so very quickly you move from the sun path analysis looking initially at the percentage of solid and glaze, whether we're fully glazed or whether we're partially glazed with spandrels, and the percentage of those spandrels, and to separate the various opaque and clear elements of the facade, we obviously have the framing elements, and those framing elements contribute a lot to not only the design of the facade system but also its energy performance. So we very quickly have to dive down into the analysis of the vision areas where we have glazing supported by framing, and the spandrel areas where we have insulation behind the glass, which are the opaque areas typically at slab edges and below desk level. And that allows us to get elemental U values of the individual components, and also then total system U values of the facade as a whole, which then inputs into our understanding of the energy flow into and out of a project. That then allows us to look again back at a macro level of the environmental systems we put into a project, so that then we can take the total solar irradiation, we can take the mechanical systems that we've chosen, we can take the facade system and iteratively tune the mechanical systems and their controls to the facade system and how we might control the shading systems that are inside and outside of that facade system. So we often use parametric modelling and optimization techniques to look at those various often conflicting criteria to understand where the sweet spot is, because certain things will be passively resolved, as we've discussed, and certain things can be actively controlled. And the sweet spot is the optimized location between often varying parameters. And sometimes it's heat gain, sometimes it's heat loss, sometimes it's daylight, sometimes it's glare. And we have to understand each of those conflicting criteria to come up with an ultimate facade solution.
Talk us through some of the emerging technologies. Where is curtain walling going to be maybe 5-10 years time?
The glass industry has moved very quickly to more and more sophisticated products that allow us to intercept the infrared, the heat energy of the sun, whilst letting the light energy through and allowing daylight through the facade. So we have some examples actually of glass here which show various products. So the shading we can put a physical barrier in the glass unit and create shading within the double glazed unit, and this gives you a static shading element which redirects light, so it intercepts the sun path but actually redirects the light within the building depending on the shape of the louvers. We can then look at interlayers. So here we have two pieces of glass which are laminated together with a dividing sheet or membrane, which is the solar control interlayer, and that is bonded into the glass in the factory to provide a single laminated piece of glass that deals with the solar gain. And it's basic infrared selective. So where we want to cut out the infrared, it's a sheet material that takes out that infrared heat and then allows us to let the daylight through. The final piece of glass here we have is one of many hundreds, if not thousands, of glass products we can choose from, which use a cocktail of coatings on the glass to provide glass that has different degrees of reflectivity, but also different degrees of transparency. So you can see the image through the glass, or my hand through the glass, versus not. So you can see that it has a blue colour in this case. Perhaps the greatest advantages of solar shading are on the coatings of glass, getting more and more neutral coatings that avoid us going for the old 70s reflective or body tinted glasses to glasses that have a much more natural appearance, letting the daylight through but intercepting the infrared.
Perfect.